Stars are born, they live, and they die. And if they die hard enough, they leave behind some of the most extreme objects in the universe. Gravastars might be one of them. But to understand what a gravastar even is, we'd need to start at the very beginning. Like the very beginning. Nebula. Before anything can explode, collapse, or get weird, something has to be born, and stars are born in nebulous, massive clouds of gas and dust floating in space, but not all nebulae are the same. Emission nebulae glow because their gas is ionized and pumping out light. Reflection nebulae don't glow on their own. They just scatter nearby starlight like a cosmic disco ball. And planetary nebulae, which have nothing to do with planets, are the shells of gas that sun-like stars puff off when they die, leaving behind a tiny white dwarf core. Take the Orion Nebula. It's about 1,267 light-years away, spans roughly 25 light-years across, and contains around 2,000 solar masses of raw material. You can see it with your naked eye. And it's just one star-forming region. Modern surveys like FANGS have cataloged over 5,400 distinct nebular regions across 19 nearby galaxies, measuring electron densities, stellar ages, and star formation rates. These aren't just pretty pictures anymore, they're hard data. But here's what matters for us. Nebulae are the opening act. Every neutron star, every black hole, every exotic object we're going to talk about started right here, as gas and dust in a cloud. So what happens when that gas starts to clump together? White dwarf. So what happens when a regular star like the sun runs out of fuel? Does it explode? Nope. It does something way less dramatic. It quietly sheds its outer layers into a glowing shell of gas called a planetary nebula, and what's left behind is a white dwarf, basically a stellar corpse the size of Earth, but with roughly the mass of the sun crammed inside it. Observed white dwarf masses cluster tightly around 0.6 solar masses, with the full range running from about 0.17 to 1.33 solar masses. Their radii are roughly 0.8 to 2% of the sun's radius. That's Earth-sized. And the density? About 1,000,000 grams per cubic centimeter. A teaspoon of white dwarf material would weigh several tons. On Earth, that teaspoon would punch through your kitchen floor, your foundation, and probably keep going. The best studied white dwarf is Sirius B, just 8.6 light-years away, practically next door. Its mass is around 0.98 to 1.1 solar masses, and its surface gravity is thousands of times Earth's. We've confirmed this directly using Hubble spectroscopy by measuring the gravitational redshift of light clawing its way off the surface. But here's the key thing. White dwarfs aren't burning anything. No fusion, no reactions, nothing. They're held up entirely by electron degeneracy pressure, a quantum mechanical effect where electrons basically refuse to be squeezed any closer together. That's it. That's the whole support structure. And for most stars in the universe, this is the final stop. Peaceful, stable, done. But what happens when a star is too massive for electrons to hold the line? Supernova remnant. So a massive star dies. It doesn't just disappear. It explodes violently, and what's left behind is an expanding shell of superheated gas and shockwaves ripping through space. That's a supernova remnant. Here's a weird stat. In the entire Milky Way, we've only cataloged about 310 of them. That's it. Our galaxy is over 13 billion years old. Supernovae happen roughly once or twice a century, and we've found 310. Part of that is because remnants don't last forever, they fade, and part of it is that space is really, really big and finding them is hard. But the ones we have found, incredible. Take Cassiopeia A, it's about 10,400 light years away, only around 340 years old, basically a baby. Its forward shockwave is still expanding at roughly 4,200 to 5,200 kilometers per second. That's fast enough to cross the distance from the Earth to the moon in under 2 minutes. The total kinetic energy locked in that expanding shell is estimated at about 2 times 10 to the power of 51 ergs, which is roughly equal to the sun's entire energy output over its full 10 billion year lifetime, all packed into one explosion's aftermath. And here's the part that gets personal. All those heavy elements forged in the explosion, iron, calcium, oxygen, they get scattered across the interstellar medium by the remnant. The iron in your blood, the calcium in your bones, delivered by ancient supernova remnants just like this one. But the explosion isn't the end of the story. Something gets left behind at the center, something dense. Binary star system. Stars don't like being alone, or more accurately, most of them never had the choice. Roughly a third of all stellar systems in the Milky Way are binary or multiple, meaning 2 or more stars orbiting each other, and that fraction depends heavily on mass. Only about 22% of the smallest, dimmest stars have companions. For sun-like stars, it's around 44%. But for the real heavyweight stars above 16 solar masses, over 80% are in multi-star systems. So for massive stars, being in a binary isn't the exception. It's basically the default. And astronomers love binaries because they're one of the best tools we have for weighing stars. If two stars orbit each other and one passes in front of the other from our perspective, you get an eclipsing binary. Combine that with Doppler shifts from their spectra, apply Kepler's laws, and you get precise masses. No guessing, no modeling, just geometry and gravity. But binaries get really interesting when one of the stars dies and leaves behind a compact object like a neutron star or a black hole. The surviving companion keeps dumping material onto the dead one. And that infalling gas gets superheated and blasts out X-rays bright enough to detect across the entire galaxy. That's an X-ray binary, and it's actually how the lightest confirmed black hole was identified at roughly 3.8 solar masses. And remember white dwarfs? Put one in a close binary where it's stealing mass from a companion, and eventually it crosses its own stability limit and detonates. That's a Type 1a supernova, the same kind of explosion astronomers use as a cosmic measuring stick to calculate distances across the universe. So binaries aren't just common, they're how we measure almost everything. Speaking of measuring things that are hard to see, let's talk about what happens after stars die violently. Neutron star. So a star goes supernova and the core collapses. If what's left over is too heavy for electron degeneracy pressure to hold up, but not quite heavy enough to become a black hole, you get something in between. The core crushes down until protons and electrons merge into neutrons, and the whole thing compacts into a ball roughly 12 kilometers across. That's smaller than Manhattan, but it contains more mass than the sun. That's a neutrine star. And we're not guessing about those numbers. There's an X-ray timing instrument bolted to the International Space Station called NICER, and it measures the precise shapes of X-ray pulses coming off neutron star surfaces. From that data, scientists can model the mass and radius of these things with impressive precision. A 1.4 solar mass neutron star comes in at about 12.2 kilometers in radius, plus or minus half a kilometer. A 2.1 solar mass neutron star, well, it's 11.9 kilometers. Slightly smaller, yeah, the heavier one is actually more compact. More mass means stronger gravity squeezing inward, which wins out over the additional material. That's how extreme the physics is at these densities, and the densities are genuinely absurd. A single cubic centimeter of neutron star material contains around 400 million tons. That's like compressing Mount Everest into a sugar cube. Central densities in measured neutron stars reach up to about 5 times nuclear saturation density, conditions no experiment on Earth can reproduce. But here's the critical number. NICER's equation of state analyses suggests that the maximum mass a neutron star can support is somewhere around 2.3 solar masses. Above that, no known force in physics can stop the collapse. So what happens when you cross that line? Pulsar. So some neutron stars don't just sit there being impossibly dense, they spin. And if a neutron star's magnetic axis doesn't line up with its spin axis, it shoots beams of radiation out into space like a lighthouse. As it rotates, those beams sweep across the sky, and if one happens to point at Earth, we detect a pulse. That's a pulsar. Now here's where it gets stupid. PSRJ 1748-2 446 AD, sitting about 28,000 light years away in a globular cluster called Terzan 5, holds the record for the fastest known spinning pulsar. It rotates 716 times per second, 716 full rotations, every single second. This thing is maybe 32 kilometers across, spinning so fast that a point on its equator is moving at something like 24% the speed of light. That's not a star. That's a blender made of nuclear paste. The second fastest, PSRJ 0952-0607, clocks in at 707 rotations per second with a mass around 1.4 times the sun, orbiting a tiny companion smaller than 20 Jupiter masses on a 6.4-hour period. These two are basically tied in a cosmic drag race nobody asked for. But here's the thing. These millisecond pulsars, the ones spinning hundreds of times per second, weren't born this fast. They're recycled. A dead, slowing neutron star in a binary system gradually pulls material off its companion, and that infalling matter spins it back up over millions of years. A dead star, resurrected by cannibalizing its partner. Astrophysics is metal, and because their rotation is so stable, pulsars double as some of the most precise natural clocks in the universe, rivaling atomic clocks. Scientists use them to test general relativity, hunt for gravitational waves, and map the stuff between stars. So we've got objects 30 kilometers wide, spinning faster than your brain can process, precise enough to test Einstein's math. But what happens when gravity wins completely? Black hole. So what happens when a collapsing core is too massive, even for neutrons to hold up? We're talking above roughly 2.3 solar masses. The answer is nothing stops it. No known force, no quantum pressure, no last-minute physics swooping in to save the day. The core just keeps collapsing, and what you get is a black hole, a region of space-time where gravity is so intense that not even light can escape. Now, a quick public service announcement: black holes do not suck. At a distance, a black hole's gravity behaves exactly like any other object of the same mass. If you swap the sun for a black hole of equal mass right now, Earth would keep orbiting just fine. You'd freeze to death, sure, but you wouldn't get pulled in. Black holes are not cosmic vacuum cleaners. They're just very, very compact, and we've actually seen one. one. In 2019, the Event Horizon Telescope, a planet-sized network of radio dishes, captured the first direct image of a black hole's shadow. It was the supermassive black hole at the center of Galaxy M87, a crescent-shaped glow 42 microarcseconds across, surrounding a central mass of about 6.5 billion solar masses. Billion. With a B, that single image turned decades of theory into observable fact. On the smaller end, stellar mass black holes show up in X-ray binary systems, where they're actively pulling gas off a companion star. The lightest confirmed black hole in a binary sits at around 3.8 solar masses, just barely above the neutron star ceiling. But the defining feature of any black hole is the event horizon. Cross it and nothing gets back out. No light, no matter, no information. It's the boundary between physics we can test and physics we genuinely cannot access. What happens beyond that boundary is one of the biggest open questions in all of theoretical physics, and it's exactly that boundary that gravastars were designed to replace. Gravastar. So here it is, the thing the video is named after. A gravastar, short for gravitational vacuum condensate star, is a theoretical object proposed as an alternative to the black hole. Not a tweak, not a minor edit, a fundamentally different answer to Einstein's equations that avoids both an event horizon and a singularity. No point of infinite density, no boundary of no return. Just a very, very weird ball of vacuum energy wearing a black hole costume. The original model, proposed by Maser and Motola, has 3 layers. Think of it like the worst sandwich ever. The interior is filled with de Sitter vacuum energy, basically a core of negative pressure where P equals negative R joule. This is the same kind of energy associated with the accelerating expansion of the universe, just crammed inside a compact object. Surrounding that core is an ultra-thin shell of exotic stiff matter, right where the event horizon would normally be, where pressure equals density, and outside that shell, normal Schwarzschild spacetime, the exact same curved geometry that surrounds a regular black hole. And that's the kicker. From the outside, a gravastar looks essentially identical to a black hole. Same gravitational pull, same warping of spacetime, same shadow in the Event Horizon Telescope. Current instruments basically can't tell the difference, so why bother? Because gravastars sidestep the singularity problem entirely. No singularity means no place where physics breaks down, which means the black hole information paradox, where information supposedly gets destroyed, loses its sharpest edge. The math works within general relativity, the model is self-consistent, but here's the honest part. No gravastar has ever been observed. Not one. The model is mathematically interesting, but mathematically interesting and physically real are separated by a canyon called evident. Gravastars remain theoretical proposals, waiting for observational tests precise enough to distinguish them from the black holes they mimic. So how would we even begin to tell the difference? Dark matter. Okay, let's zoom out, way out, because everything we've talked about so far, nebulae, white dwarfs, neutron stars, black holes, gravastars, all of it, every single object you can see or detect with a telescope, makes up about 5% of the universe's total mass and energy. 5%. That's it. You, me, every star, every planet, every galaxy, every grain of dust, every photon of light, all of it is 5% of what's actually out there. So what's the rest? Well, roughly 27% is something we call dark matter. It doesn't emit light, it doesn't absorb light, it doesn't reflect light. No one has ever directly detected a dark matter particle. Not once. Not in decades of trying with underground detectors, particle colliders, space telescopes, nothing. But we know it's there, because we can see what it does. Stars at the outer edges of galaxies orbit way too fast. Like, absurdly too fast. If the only mass holding those galaxies together were the stuff we can see, those outer stars should fly off into the void. They don't. Something invisible is providing extra gravitational pull, and it's providing a lot of it. Galaxy cluster dynamics show the same thing. Cosmological measurements show the same thing. Every independent method points to an unseen mass component roughly 5 times larger than all the baryonic matter in the universe combined, and not every dark matter claim has survived scrutiny. ESA's integral Lagrange ray observatory once picked up a signal from the Milky Way, a 511 kilo electron volt positron annihilation line that some researchers suggested could be a dark matter signature. Turns out it's better explained by radioactive decay from massive star supernovae, science correcting itself. That's what's supposed to happen, but the big question, what dark matter actually is, remains completely open. We know it gravitates, we know it's everywhere, we know it outweighs everything we've ever seen or touched by a factor of 5, and after all of that, we still have no idea what it's made of. So what do we actually know? And more importantly, what don't we know? Singularity. So what's actually at the center of a black hole? The honest answer is, we don't know. And that's not a cop-out. That's the physics. In classical general relativity, a singularity isn't a place you can visit or a thing you can point at. It's where the math breaks. Space-time curvature goes to infinity, the equations stop producing meaningful answers, and the theory basically throws up its hands and says, I got nothing. In a non-rotating rotating black hole, the singularity isn't even a location in space. It's a moment in time, a future boundary that all infalling matter must reach. In a rotating black hole, the math describes something shaped like a ring. But none of this is observable because singularities are hidden behind event horizons. No information gets out, ever. And here's the thing. The Penrose-Hawking singularity theorems prove that these aren't rare edge cases. Singularities show up generically whenever matter collapses past a certain point under realistic conditions. The theory predicts its own breakdown. General relativity is basically saying something happens here, but I'm not the one who can tell you what. That's the seam where a quantum theory of gravity has to take over, and we don't have one yet, which brings us full circle. GRAVASTARS exist as a theoretical proposal precisely because they dodge this problem. No horizon, no singularity, just a vacuum energy interior and a thin shell doing all the heavy lifting. Whether that's what actually forms when a massive star collapses, or whether singularities really do lurk behind every event horizon, remains one of the most important open questions in physics. We started with clouds of gas, we end at the edge of what we know. If you enjoyed this video and want to see more, click the video on the screen now.